Okay, this is question 5 on the HL physics mock. This is quite badly misunderstood by quite a few people. So it's about internal energy and thermal energy. The first one is just a definition question. Write your definition for internal energy and write your definition for thermal energy. There are 3 marks available. The first mark is for internal energy, and that's the total kinetic energy and potential energy of the molecules of a body or an object or whatever. And most people got that one right, but we didn't all get thermal energy. This is just a textbook definition, which you've just got to remember. Thermal energy is the net or total amount of energy transferred between 2 bodies at different temperatures. That's how we define thermal energy. And if you don't know that, if you don't remember that, you've got to include that in your revision, your quiz cards or whatever, and make sure you remember those definitions. The next part is to describe with reference to the energy of the molecules the difference in internal energy of a piece of iron and the internal energy of an ideal gas. And the key point here is that it's an ideal gas. So again, the first part most people got right. The internal energy of the iron is equal to the total kinetic energy plus the potential energy of the molecules, just following on from part A. But the ideal gas, some people slipped up on because ideal gases only have kinetic energy. They don't have any potential energy, so the internal energy is just the total kinetic energy of the molecules. But again, it's just 2 definitions. You should write those 2 definitions. You should pick up both marks. Part C is the first. Is there some calculations? We start off with some calculations. It gives us information that we're used to seeing about data, basically from water and iron. And we're going to eventually work out some temperature changes and energy transfers. The first part is to state an expression in terms of theta, which is the energy change, is the maximum temperature of this piece of iron, which is in a kiln, and all the other data. And what we're looking for is an expression you can see here, 60 multiplied by the difference between that maximum temperature and 45. To explain that, we have to imagine that the piece of iron is going to go from that maximum temperature theta down to its final temperature, which we have to identify, to realize is going to be the final temperature of the water. It's 45 degrees here. So it's going to change from whatever temperature it was down to 45 degrees. That's the temperature change we see here. You multiply that temperature change by the thermal capacity of iron, which is 60 joules per Kelvin, and we will end up with the energy transferred from the iron into the water. As a quick example, which you don't need to do to get the mark, I've written it like this. So if we imagine the kiln was 145 degrees, then the iron will cool down from 145 down to 45, making an temperature change of 100 Kelvin or 100 degrees C. Multiply that by 60 joules per Kelvin, and we get an energy transfer of 6,000 joules. So in this question, it doesn't really matter whether you use degrees C or Kelvin, it'll be fine either way. But if you use Kelvin, you have to convert the 45 to Kelvin as well. But for the expression, it's not important. The second part to this is to calculate the increase in internal energy of the water as the iron cools in the water. So this one is slightly more difficult because there are more numbers, but that might help us to get our head around it. So first of all, they've identified 29 Kelvin or 29 degrees C as the temperature change of the water. That's starts at 16, ends up at 45, so it's gained 29 kelvins of temperature. So we multiply that by the thermal capacity of the water, and we get the increase in internal energy of the water. That's the energy that was transferred into it from the hot iron. Okay, and it's important to understand that for the third part of this question. The third part is to determine that starting temperature. And to do so, we need to understand that this is the energy lost by the iron over here. This is the energy lost by the iron here, and this is the energy gained by the water. Now, in a perfect situation, those 2 are equal. So that's what we've got for the first line. The first line is to appreciate that those 2 are equal. Second line is to do the calculation, and you should get 1000 degrees C, and they've accepted 1010 degrees C if you do it to 3 significant figures. Now, a lot of people made some errors here. You talking about kelvins, which wasn't necessary in this question. You can do it all in degrees C. It's just talking about temperature changes. But again, it's possible with Kelvin, it's just slightly more complex. So if you're not sure how to do it, if you didn't get it right the first time, try it again, just stick with degrees C, and you should find yourself the right answer. Okay, and that is question 5.